My name is Ian Hill. I'm the Director of Product Development for the Open Architecture Group at DRS Signal Solutions. My assumption here is that most of you come from a processing/digital design background. I'm going to talk about high-performance RF, how we can intelligently integrate that into your ecosystems so that we don't stifle creativity, but yet we provide the scalability that the customers are looking for. Briefly, we started in 1960 as CEI. You might better know us as Watkins Johnson. We were Watkins Johnson for 35 years. We've had a series of purchases. We're acquired by a series of companies. Today we're DRS Technologies. We've been that for 13 years. Still the same focus, though, is high-performance RF front ends. So this slide briefly shows density versus time for the same or improving RF performance. Certainly smaller, low-power radios do exist today. To show you where we are with that, I show two 9158 6U V&V modules. These are high-performance microwave tuners. Within 6 years, we've actually integrated those into one single 3U VPX card. An incredible improvement in density, power, and size, and weight. Okay. Consider these two red cars. They are obviously both not the same. Point here is that size, weight, and power are not the only metrics. I actually drive the one on the left, unfortunately. So for RF design, there are three key specifications for high-performance RF that we focus on. Noise figure, how sensitive is your RF? Overload, how large of signals can you actually handle? And spurious, the number of false signals you see. These are exceptionally important to our customers. They're not going away. In fact, they're getting more important because of the crowded environment we see today. We have a lot of underlying specifications we also track, but they're really there to support those big three. So it's very easy to get excited about some key approach. And I often have customers come ask me, what is your mixer you're using, or what A to D? The fact is, it takes away from the target, which is get the signals you want and reject the rest. We've all been there. So to just hit this home a little bit further is our focus at DRS Signal Solutions is getting the small signal in the presence of very large signals. So again, back to this slide you've seen before, you have this integration to a 3U VPX card. Not only reduced the size and the power and the weight, but we also extended the temperature range, increased the dynamic range, and extended the frequency. So this is the trend industry is looking for. So we talked about swap. We talked about performance. I want to talk about system longevity. System starts off design and funding. That's a long process. Acquisition, installation, and then training. And then you finally get to use the system. So it's really important that you can have the longest installation possible because the upfront is so expensive. So why does a system meet end of life? Well, the fact is there's fielded equipment that just cannot get the signals that are currently out there. They're too expensive to operate. You can't have an operator behind every signal anymore. There's a lack of parts. The system works fine, but you just can't support it anymore, and there's no manufacturer support. So this is where it would end, but you guys have all worked on ecosystems. The whole point is to extend the life, and that has to be done smartly, especially with high-performance RF. So some technology is moving very quickly. The cell phone, every 2-3 years it changes. Some technology, it's going to be around for a while. It's much longer. So we need to anticipate future needs. The whole point here is that there's definitely a trend towards multi-mission capability, and this really requires flexible and adaptable hardware, and it requires good partition and breakpoints. As I said, multi-mission capability, rapidly customizable, flexible, extendable, upgradable. So you've created MOSA-type architectures And these are the building blocks. You have software configurable missionware. You can change from a SIGINT mission to an SIGINT mission to, let's say, an EW mission on the fly. And then you have service-oriented architectures, the glue that hold everything together. But the plug-in modularity is very important here. So where we are, we're able to put this high-performance RF into these little modules because of higher density SMT, improved semiconductor parts, improved packaging, and improved interface and standards that you've supplied us with. So wait, what about the upgrade impact of whiz-bang technologies? So first one I want to talk about, and these are technologies that actually would give you a step function, for example, in capability, and really change the way you might integrate into the system. Laser optical RF converters. They offer extremely wide bandwidth, 4 gigahertz or more. Unfortunately, current state-of-the-art optical converters, which we've looked at, it's a disruptive technology, still provide only about 56 dB of dynamic range. For some applications, that might be perfect. For the applications our products are usually in that our customers are demanding, that's not good enough. Additionally, there's temperature and vibration are major technical challenges. Zero IQ receiver on a chip. This technology touts very small, very low-cost capabilities. This has been around for about 60 years. Unfortunately, it has the same problem, which is spurious. This is just a physical constraint in the analog circuitry. And so here I'm showing 2 radios. One is a superhet, and one is a best-in-class zero IF. Clearly, you can see all the spurious that it's creating. Now, for some applications, that's OK. However, for wide frequency coverage, wide bandwidths, that's very difficult to dynamically get rid of. And then high-speed ADCs for direct digitization. The fact is, above 100 megahertz, as you get towards a gig, you see orders of magnitude difference between a superhet, downconvert, and directly digitizing. That is asymptotically reaching a point where they're not getting much better, especially below, let's say, a gigahertz sample rate. So now, if you believe that we still have to integrate these heterodyne approaches, there's no gee whiz gadget out there in the foreseeable future, how will we smartly do this? And this is about breakpoints. So this quickly shows, actually, very simply, the basic building blocks of a system. You have the RF converter, the AD, and then the signal processing piece of it. The RF converter changes fairly slowly. The analog, there's talk about, should we put the A to D on a mezzanine card, for example? Well, the fact is, if you've probably integrated your A to D with the RF, you will probably not see many gains by pulling that out in the future and putting a new one there, because they're simply not getting that much better, especially below a certain sample rate. Digital processing is improving very rapidly still, however. They're following Moore's law. High-end servers are commodity items. So to me, a logical breakpoint for a lot of applications is actually between the A to D and the digital signal processing realm. So if you're going to talk about that, you need to talk about data formats, electrical interfaces, and mechanical interfaces. What are the standardizations that's going to allow rapid integration for our customers? So going into a little bit more detail, I'm showing more of a radio here. I'm still the same breakpoint. So VITA 49, a data format, it's really about the language we speak. It makes the radios agnostic. You can have many radios from different vendors all speaking the same language to the back-end processing. This is an industry-adopted standard. All of our radios that digitize come with it. It's a very simple standard. It talks about signal data packets and then context data packets. They contain frequency, precision time tagging, channel number, gain. So it gives all the information you on the back end could need. It's also flexible. So how do we physically connect the modules? So this is where a lot of people out here are much more educated in this area. There's a couple standards. I'm going to talk about Ethernet very briefly. PCI Express is another good one, commercially driven. So Ethernet is well established. Standard speed 10 gigabit per second. 100 gig is now available. TCP/IP for crowded links. You have a UDP option. You have wired for short distance, and you have optical for longer hauls. RF, connecting the RF. This isn't changing very quickly. There's a few standard type of coaxes that are widely used. So now let's talk about the plug-in module. These are actually the ecosystem, the Legos that create the system. VME and VIXI were standards we used yesterday. It looks like VPX, especially in the DoD area, is the standard that's moving forward because there's many features. Really, it defines two types of cards, a backplane, obviously, but they're the 3U and the 6U card. They're relatively compact. They're conduction cooled, high-speed backplane, and we can provide coax through the VITA 67.3 standard, which I believe provides a lot of flexibility to the board designers. So I want to talk about 67.3 for a second. It's the newest standard out. From a consumer point of view, it really talks about only two things: the size of the hole and the position of that hole on the backplane. So as a user, if you're buying a card from another vendor to upgrade that, the vendor only has to provide you with the mating plate that goes into a standard hole. Has a lot of benefits. These are also true for .1 and .2 standard. I want to talk about briefly one of the bigger benefits is that the actual contacts within the housing are not specified, the number nor the positions. So for the board designer, this creates a lot of flexibility to design his board the way they want to. So problem with over-constrained standards. So we've looked at putting RF on XMC or FMC cards, and there's other standards driving RF integration into the VPX module itself. There's a lot of problems with this. It adds an additional breakpoint. I think the VITA 67.3 is a nice place to do it. The fact is, I can make a tactile box more efficient than an open architecture box, but I give up a lot of flexibility. You wouldn't want to duplicate that yet again. RF is an extremely tricky thing to do. It's different than the digital, particularly in regards to spurious and performance, high performance RF. VITA 67.3 is pluggable. This sort of constraint is unnecessary. We're offering now cards with more density than we could have gotten if we were constrained further within the VPX housing. So to give you an example, this is a Vesper. It's an EDM right now. It's actually a 10-channel receiver system. Each channel is a high-performance RF front end. It covers 20 meg to 6 gigahertz, 100 gigahertz of bandwidth. We build Legos with inside that Vesper module for future product instantiations and upgradability, such as frequency. None of this would have been possible had we tried to put this on another standard such as XMC or FMC, or drive the standard further into the VPX module. How do you deal with something like a vibration-isolated OCXO if you're constrained to a little area? How do you deal with spurs? How do you lay out your boards? How does your mechanical pieces interconnect? If you take all that away, I think that you're not going to get the quality you're looking for. So upgrade path briefly. Identify your core system elements: antenna, tuner, processor. Identify easy upgrade parameters. Bandwidth, that's a nice one. Frequency, number of channels, signal processing. And then choose good system interface breakpoints, RF and data. And then in conclusion, choose carefully for the future. You will be living with your choice for a long time.